Welcome to this presentation on atomic structure. In this session, we will explore the basics of atomic composition, the significance of atomic and mass numbers, electron configuration, isotopes, and the calculation of relative atomic mass. Atoms consist of three key subatomic particles: protons, neutrons, and electrons. Protons and neutrons reside in the nucleus, which forms the atom's dense core. Electrons, much lighter in mass, orbit the nucleus in defined energy levels. These particles work together to define the identity, stability, and behavior of the atom. The atomic number, denoted by Z, is fundamental to an element's identity. It equals the number of protons in the nucleus, distinguishing one element from another. For instance, hydrogen with Z equals 1 has 1 proton, whereas carbon with Z equals 6 has 6 protons. This number is unique to each element and is central to the periodic table's arrangement. The mass number, represented by AAA, gives the total count of protons and neutrons in the nucleus. While protons determine the element, neutrons contribute to its isotopic variation. For instance, carbon has a mass number of 12, with 6 protons and 6 neutrons in its nucleus. Electron configuration reveals how electrons are distributed among an atom's energy levels or shells. Using rules such as the Aufbau principle, we know electrons occupy the lowest available energy levels first. For example, oxygen's configuration is 1s22s22p4, indicating 8 electrons arranged across 2 shells. Isotopes are variations of the same element with identical proton counts but different neutron numbers. For instance, hydrogen has 3 isotopes: protium, deuterium, and tritium. While their chemical properties remain the same, physical properties, such as density or radioactivity, can differ. The relative atomic mass of an element is the weighted average of all its isotopes, considering their masses and natural abundances. For example, chlorine's isotopes, Cl35 and Cl37, combine to give an average atomic mass of 35.5. Let's walk through the calculations for 3 different examples of relative atomic mass, one step at a time. Example 1. We are given an element with 2 isotopes. Isotope 1 has a mass number of 35 and an abundance of 75%. Isotope 2 has a mass number of 37 and an abundance of 25%. The formula to calculate relative atomic mass is relative atomic mass equals mass of isotope 1 multiplied by its abundance plus mass of isotope 2 multiplied by its abundance divided by the total abundance, which is usually 100. Substituting the values, we have multiply 35 by 75. This gives 2,625. Multiply 37 by 25. This gives 925. Now add these 2 results together. The sum is 3,550. Divide this by 100, as total abundance is 100%. The result is 35.5. Therefore, the relative atomic mass of the element is 35.5 unified atomic mass units. Example 2. In this example, the element has 3 isotopes. Isotope A has a mass of 10 unified atomic mass units and an abundance of 40%. Isotope B has a mass of 11 unified atomic mass units and an abundance of 50%. Isotope C has a mass of 12 unified atomic mass units and an abundance of 10%. We follow the same formula. Multiply 10 by 40. This equals 400. Multiply 11 by 50. This equals 550. Multiply 12 by 10. This equals 120. Add these results together. 400 plus 550 plus 120 equals 1,070. Divide this by 100. The result is 10.7. Therefore, the relative atomic mass of the element is 10.7 unified atomic mass units. In this case, the relative atomic mass of the element is already provided as 50. The element, called X, has 2 isotopes. Isotope X49 has a mass of 49 and an abundance of 80%. Isotope X51 has a mass of 51, but its abundance is not explicitly given. We know the total abundance must equal 100%. Therefore, the abundance of X51 is 20%. Now, substitute these values into the formula. Multiply 49 by 80. This gives 3,920. Multiply 51 by 20. This gives 1,020. Add these values. The total is 4,940. Divide this by 100. The result is 50. This confirms the relative atomic mass of element X as 50 unified atomic mass units, consistent with the given data. In summary, understanding atomic structure involves recognizing the roles of protons, neutrons, and electrons. Atomic and mass numbers provide insight into an element's identity and isotopic variations. Together, these concepts form the cornerstone of chemistry and atomic theory. Thanks for watching. To deepen your understanding of SI units, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concepts effectively and enjoyably.